Hello everyone, I'm Cong Liang from Tsinghua University. Today, I'm going to talk about our work, NegotiaToR. With more and more applications running in the cloud, traffic demands in DCNs increase rapidly. Electrical packet switching faces capacity limitations in the post-Moore's law era. To address this, optical switching with its high capacity and low cost has drawn researchers' interests. Unlike packet switching, here to send data directly to a different set of destinations, the topology needs to be reconfigured first. Recently, the reconfiguration delay has decreased from several microseconds to several nanoseconds, which is sufficient for fast reaction to the dynamic traffic patterns among TORs. And here's how such AWGR-based fast switching hardware works. At sources, the tunable lasers tune their wavelengths and synchronously send data. Then the AWGRs forward the data to different destinations according to their wavelengths. And here is another reconfiguration. Other than the ultra-low reconfiguration delay, it can also expand to the DCN scale using flat topologies above TORs, which is one-layer AWGRs. For high port count AWGRs, we can use the parallel network topology, where each AWGR connects all TORs. While for low port count AWGRs, which are more accessible, we can use the SIGCOMM' topology as a practical alternative. With fast reconfiguration and DCN scalability, fast optical switching hardware seems to be ready for DCNs. The next problem is how to schedule these fast reconfigurable optical links. To schedule the links, we are actually talking about getting non-conflicting paths from sources to destinations, since optical links are bufferless and the conflicts will cause data damages. Also, to leverage the fast switching hardware, we hope the scheduling is rapid to enable fast reaction to dynamic traffic patterns. One solution is traffic oblivious, which reconfigures the network simply according to predefined round-robin connections. This schedulerless design is practical, which is important when it comes to industrial deployments. However, due to the mismatch of the topology and actual traffic demands, it suffers from sacrificed latency and throughput. Another solution is on-demand, which reconfigures the topology according to real-time traffic demands. It can potentially provide better latency and throughput. However, despite the potential performance gains, there exists practicality concerns due to the fast on-demand scheduling requirement. A centralized scheduler can do the job, but will introduce excessive complexity. So we pass that design decision and ask this question. Is there a practical yet high-performance on-demand distributed scheduling architecture for reconfigurable DCNs? This task is challenging. Firstly, scheduling often leads to reduced practicality due to the scale of DCNs and the dynamics of traffic demands. Measurement of flow-level information and the calculation like ordering by size both increase implementation complexity, especially under the context of fast scheduling at DCN scale. Then, to support a distributed scheduling algorithm, TORs should frequently exchange scheduling messages with each other, while avoiding conflicts with data transmission in the optical links. A separate control plane network can solve the problem, but at a significant cost. Finally, ensuring low latency of mass flows, particularly when incast happens, is challenging in scheduling. As long as the scheduling delay exists, mass flows cannot be sent promptly, which leads to downgraded latency. For deployment practicality, following the principle of Occam's razor, we present NegotiaToR, which is tailored towards a simple yet effective design. Regarding these three challenges, NegotiaToR matching algorithm is designed towards minimalist on-demand scheduling on flat topologies. And we use two-phase epochs to support one-hop direct data transmission as well as in-band pipeline scheduling. We also provide opportunities to bypass the scheduling delay to optimize FCT for mass flows even under incasts. Next, we will go into the matching algorithm first. There are two kinds of conflicts when scheduling the optical links among TORs on flat topologies. And because there is only one layer of AWGLs in between, we can actually consider this as a matching problem. Similar problems have been seen in crossbar packet switches decades ago. For each switch to forward packets, it needs to get non-conflicting input-output matches. A lot of works have been done in this area, and they have been proven fast and practical, along with extensive implementation experience. Inspired by one of these works, RRM, we present negotiator matching, which focuses on TOR level matching over flat topologies. Let's see an example on the parallel network topology first. Each port can receive from all other TORs, and we should choose one from all possible sources. Each TOR has multiple ports, and we need to schedule them simultaneously. Now, we assume TOR1 has traffic to send to TOR2. Meanwhile, TOR3 has traffic to send to both TOR2 and 4. The first step of negotiator matching is TOR level request. Sources check their local queues and send binary requests representing traffic demand to their destinations without data side or priority information. Now, the destinations are aware of the requests from multiple TORs. To avoid collisions at the destination side, they need to pick one request for each port. To this end, inspired by RRM, we use a round-robin grant ring to allocate ports to these requests. Take TOR2 as an example. The position of the ring's pointer represents the highest priority source, with priority diminishing in a clockwise direction. After granting one source, the pointer is updated to the next source of the round-robin schedule, effectively ensuring fairness and avoiding starvation in port allocation. To further improve fairness, all ports share the same ring. TOR2 then allocates requests to all ports with this ring in turn. As for TOR4, there is only one request. The grant ring just allocated to all ports. After port level grant, destinations send the grants back to sources. And here comes source side conflicts. The sources use per port accept rings and accept one grant for each port. This marks the finish of one negotiator matching scheduling process. The accepted grants indicate a set of non-conflicting matches. And then tunable leaders and sources tune their wavelengths according to locally derived scheduling results with no need for result delivery. Negotiator matching can also be adapted to other flat topologies. Take the SIGCOMM' topology, for example. Unlike the parallel network topology before, in the SIGCOMM' topology, each port can only receive from a subset of TORs. So we need to modify the rings to match the topology's capability. For example, since port 1 of TOR3 can only receive from TOR1 and 2, we give it a per port grant ring with only TOR1 and 2 in it. Negotiator matching that is adapted to the SIGCOMM' topology. Now we have the distributed scaling algorithm itself. To support its running, TORs should frequently exchange scaling messages with each other. This requires full match connectivity among all TORs. To this end, we follow previous practice, use fast round-robin reconfigurations to connect all source destination TORs once. The intuitive solution works like this. First, the network is reconfigured to predefined round-robin matches, sources that can send requests to destinations. However, it takes time for destinations to receive the requests, which is the one-way delay between TORs. Only after this delay will the destinations receive the requests. Similarly, There also exists a delay between grants and the final accepts. TORs can only wait during the one-way delays, leading to link waste and thus performance degradation. To solve this, instead of running only one scheduling process at the same time, we run 3 of them simultaneously. This way, we can get a set of accepts after each round robin, and the data transmission can be done immediately after these accepts. This forms NegotiaToR's two-phase epoch. TORs in NegotiaToR are time synchronized and run in such epochs. Each epoch is a fixed time interval and is composed of 2 phases, the predefined phase and the scheduled phase. All reconfigurations happen in the predefined phase, establishing full mesh connectivity, supporting pipeline distributed scheduling. In one scheduled phase, the links keep fixed, establishing on-demand connections, sending data through one-hop paths. The pipeline scheduling design can help to fully utilize the links for high throughput. As for latency, mass flows can suffer from scheduling delays. Imagine a source-destination TOR pair that has no traffic to send before. After new traffic arrives, it requires at least 2 epochs before data transmission, even in lucky cases. When conflicts occur, the scheduling delay may be longer. This leads to long mass flow FCT, and things get worse under incasts, adversely impacting application performance. If we can bypass scheduling delays and ensure timely transmission for mass flows, their FCT could be optimized. This leads to our scheduling delay bypassing design. Recall that full mesh connectivity is provided in the predefined phase by round robin. It serves as a control plane, supporting exchanges of scheduling messages. This is actually a perfect opportunity if some source destinations have urgent data to send. We utilize this opportunity and piggyback small data packets along with the scheduling messages. Such unscheduled transmission opportunities are sufficient for latency-sensitive mass flows, which are small in size. Unscheduled transmissions are promised in each epoch and are not affected by scheduling results or workloads. Incasts can thus also be handled by them. One problem arises. What if mass flows are header-line blocked by elephant flows? To avoid such waste, we can prioritize mass flows as sources, for example, using information-agnostic mass flow prioritization, like PS. Now the main parts of NegotiaToR have been presented. We'd like to emphasize the design efforts towards practicality. NegotiaToR matching is inspired by RRM in cross-bar packet switch scheduling, which means it can borrow the proven implementation strategies from RRM, for example, implementing the RINs with programmable priority encoders. Meanwhile, NegotiaToR's other simple designs also improve its practicality, like no iteration, no data relay, binary requests, and stateless scheduling. However, this raises an important question. Could a more complex design significantly improve NegotiaToR's performance? An example is, what if we add iterative scheduling? This is also the practices in crossbar switches. We show that this is not a good choice for NegotiaToR, and the main reason is that, unlike inside the switches, NegotiaToR has a longer delay between consecutive steps. When there is no iteration, it takes at least 2 epochs for requests to get scheduled. However, when we use 3 rounds of iterations, this is enlarged to 6 epochs. During the scheduling process, the corresponding data or requests may have already been sent. As a result, the requests are now outdated. If links are reconfigured following the results, it will cause link waste and thus lead to possibly downgraded performance. And this has been confirmed by our experimental results. We have also done other similar explorations, and the NegotiaToR finally converged to its current form. Please read our paper for more explorations. We briefly show the main evaluation results of NegotiaToR. Simulations are set to contain 128 TORs connected by both parallel network and synchrous topology. We followed a series to implement the traffic oblivious scheme and provide 2 times speedup for it at NegotiaToR. For practicality, results without mass flow prioritization are also shown. Results show that NegotiaToR achieves both small mass flow FCT and high throughput on 2 representative flat topologies. Particularly, the FCT on mass flows is 1 to 2 orders of magnitude better than the traffic oblivious scheme. To sum up, we present NegotiaToR, an on-demand reconfigurable DCN architecture towards a simple yet effective design. It schedules the network with NegotiaToR matching, an algorithm designed towards minimalist on-demand scheduling on flat topologies. Inbound pipeline scheduling and one-hop direct transmission are run over 2 phase epochs. A scheduling delay bypassing scheme is also introduced to optimize FCT for latency-sensitive flows. By exploiting the fast optical switching technology to provide high performance with low complexity, we hope that NegotiaToR can facilitate the development of next-generation reconfigurable DCNs. Thank you.